All right, 8.2. I like to move this lesson out of chapter 8 and into chapter 3 because it goes so nicely with what we've been doing for derivatives and just finishing up. We can kind of tie a bow on derivatives before we're ready to move on to how we apply derivatives in real life situations. So that's why this is here. We're going to look at what L'Hopital's rule is and how you would use it repeatedly if necessary. L'Hopital's rule applies only when you have situations that are indeterminate. So the indeterminate form 0 over 0, infinity over infinity, and then infinity times 0, and the subtraction indeterminate form, and then some power indeterminate forms as well. Okay, 1 to the infinity, 0 to the 0, and infinity to the 0. So those are the 7 indeterminate forms, and L'Hopital's rule applies to all of them. So what L'Hopital's rule says is that if f and g are both 0, which would form the indeterminate form 0 over 0, then that is called that indeterminate form. And so when we get that, then L'Hopital's rule says, all right, then move on and take one round of derivatives. So this is not the quotient rule, it's a separate rule, L'Hopital's rule, and the numerator and denominator are differentiated separately. If that doesn't work, then you do a repeated derivative as many times as you need to till you don't get an indeterminate form anymore. So that's where this L'Hopital's rule second form comes in, where you've got f to the n. Okay, that is indicating repeated iterations of L'Hopital again until you don't get 0 over 0, till you get something else. You still have to verify that L'Hopital's rule is needed. You have to show that it's indeterminate. So we would start this by just substituting, and we'd say 4 plus 0 minus 2 over 0. So rad 4 minus 2, so 0 over 0. So clearly state that the indeterminate form is achieved, and so therefore L'Hopital is validated, that you can use it. So then go back and set up your limit again, and we'll use the first round of derivatives. So the derivative of the square root of 4 plus x is 1/2 times the quantity 4 plus x to the negative half times the chain rule of 1 over 0. Over 1. Then I plug 0 into that. So I'll have 1/2 times 4 plus 0 to the negative half. That's 1/2 times 1/2, which is 1/4. So this limit value had a value of 1/4. Here's another example where we'll end up with an indeterminate form. When we substitute 0 in, we're going to get 0 minus the sign of 0 over 0 cubed. So again, 0 over 0, which means we're justified in using our indeterminate, justified in using L'Hopital for the indeterminate form. So I take my first round of derivatives, 1 minus the cosine of x over 3x squared. That's 1 minus the cosine of 0 over 3 times 0 squared. That's 1 minus 1. So I get a second indeterminate form, which means I'm justified in applying L'Hopital's rule again. So my derivative would be positive sine of x over 6x, which is the sine of 0 over 6 times 0, which is still 0 over 0. And that's the strength of L'Hopital's rule, is that you can continue applying it until you get to the point where you no longer have an indeterminate form. So finally, my last round of derivatives, positive cosine of x over 6. So now I'll have the cosine of 0 over 6, and I finally get my first non-indeterminate form, which is 1/6. All right. You can use L'Hopital's rule for one-sided limits as well. When we substitute in the sign of 0 from the left over 2 from the 2 times 0 from the left, I still end up with 0 from the left and 0 from the left, which is an indeterminate form. So you can still apply L'Hopital's rule in this situation. We're just applying it to one side. And so the derivative would be cosine of x over 2. And the cosine of 0 from the left over 2 is 1/2. Or 1 from the left, technically. All right, so that's the indeterminate form 0 over 0. Let's look at some of the other indeterminate forms. Here we have x approaching pi. And so we have the cosecant of pi, which is an asymptote, and 1 plus the cotangent of pi, which is also an asymptote. So we've got infinity over 1 plus infinity, or the indeterminate form, infinity over infinity. So because the indeterminate, we've achieved another indeterminate form, we're going to use L'Hopital. So we take our first derivative. The derivative of cosecant is negative cosecant cotangent. And the derivative of 1 plus cotangent is negative cosecant squared. So this can reduce. So I'll have the negatives reduce, I'll have cosecants reduce. And then I'm going to reduce again using trig identities. So cotangent is cosine over sine. And then cosecant is 1 over sine, but I'm going to multiply by the reciprocal instead, so that I can reduce the sine function. So then I can plug in the cosine of pi, which is -1, and I get a value that's not determinant, not indeterminate. It is determined. Okay, how are you guys doing? Okay, so far? All right. So here's the indeterminate form infinity times 0. So I'm going to plug in. I'm going to get 2 times infinity times the sine of 1 over infinity, which is 2 infinity times the sine of 0, which is infinity times 0, which is an indeterminate form. The reason that is indeterminate is because there are 2 conflicting rules here. We have one rule that says anything times 0 is 0, and we have another rule that says anything times infinity is infinity, and these 2 rules conflict, and so the answer is neither 0 nor infinity, but an indeterminate form. All right, when you have a form like that, it is helpful to do some substituting. And one helpful substitution is to replace a with 1 over x. So when I do that, I would also be replacing a with 1 over x. I would also be replacing x with 1 over a. Are you replacing it with its reciprocal? So now this is going to turn into the following limit. 2 is now times 1 over a. The sign is of regular a. And now what the approaching part is. I'm replacing, if x is replaced with 1 over a, then x approaching infinity is replaced with a approaching the reciprocal of infinity, which is 0. So I just replaced all of my x variables and I replaced the approaching value. And what that does for me is it creates the following limit: 2 sine a over a as x approaches 0. Now when I plug 0 into this, I get 2 times the sine of 0 over 0, which is 0 over 0, which is an indeterminate form that justifies me using L'Hopital. So now I can go back and use L'Hopital, and I'm going to use L'Hopital always on the form that's in a fraction. You have to have a numerator and a denominator distinctly, and that's what you'll apply L'Hopital to. So a approaching 0, and the derivative would be 2 cosine a over 1, which would be 2 cosine of 0, and so the answer to this limit is 2. All right, then the other indeterminate forms we're going to see are the power indeterminates. So 1 to the infinity, 0 to the 0, and 0 to the infinity. And notice here the introduction of the idea of the natural log. So for these indeterminate forms, we're going to go back to the idea of how a natural log can help us. And we'll apply a natural log first, and then we'll do our L'Hopital. So here's an indeterminate form. If we plug in infinity, we're going to get 1 plus 1 over infinity to the infinity. That is 1 plus 0 to the infinity, or 1 to the infinity. So again, this indeterminate form is where you have two conflicting rules. One rule says 1 to any power is 1. But another rule says anything to the infinity power is infinity. Well, this can't be both 1 and infinity at the same time. So this is an indeterminate form. So we start out this way. I'm going to set this problem equal to the letter L to stand for the limit work I'm going to do. Then I'm going to do an ln in front of both of those. So an ln in front of this one and an ln in front of that. That allows me, oops, I switched the order. Let me fix that. My limit, and then my ln would go here. So that allows me to pull this x down in front. So we'll have the natural log of the limit we'll have x times the ln of 1 plus 1 over x. And then I would recommend doing another one of those substitutions here, because now you would end up with infinity times 0, right? If I plug this in, I'll have infinity times the natural log of 1 plus 1 over infinity, which is infinity times 0. So now substitute and do the same thing you were doing before, and we did in the previous problem, a to be equal to 1 over x. And then x would be equal to 1 over a. So I'll have the natural log of the limit is equal to the limit. X would be 1 over a. The natural log would be 1 plus a. And now I'm going to have a approaching 0. And the benefit of doing that is that now the 1 over a can be written as a denominator. So I'm going to erase it. And now you can do L'Hopital because now you have a fraction. So it always needs to be in the form of a fraction to do L'Hopital. This is 0 over 0, which allows me to finally use my derivative rules. So natural log of L is the limit as a approaches infinity, a approaches 0. And now I can do my derivatives. And the derivative of the numerator is 1 over 1 plus a times the chain rule of 1. And the derivative of the denominator is 1. And so the answer to all of that is 1. I knew I was going to run out of room, so I gave myself another blank slide. If you have more room to go, that's fine. But so what we've got right now is that the natural log of L is equal to 1. And so one final simple step to solve for what L is to apply e to both sides. And so the limit we're looking for is e in this question. So all of that just to get e. All right, the second to last indeterminate form we're going to look at is x to the x. And we're going to use the natural log again here. So we end up with 0 plus to the 0 plus, so that's 0 to the 0 as an indeterminate form. So I'm going to set up the natural log of the limit. And I'm going to pull x to the front, and I'll have natural log of x. In this case, if I plug 0 in, I'm going to get 0 plus times the natural log of 0 plus, which is 0 plus times negative infinity, which is an indeterminate form. So I'm going to use my substitution again, but I'm going to do it the opposite way. I am going to put a fraction in instead of taking a fraction out. So I'm going to substitute a to be 1 over x, and then x would be 1 over a. So what I'm going to get now when I do that substitution is I'll get 1 over a times the natural log of 1 over a, and a is going to approach infinity. If x approached 0 from a positive side, then a is going to approach infinity from a positive side as well. And this allows me to use L'Hopital because now I have a fraction. I didn't have a fraction before, but now I have a fraction. The fraction is key. Because this indeterminate form, let me put the a in the denominator, I'll get the natural log of 1 over infinity. That's the natural log of 0 over infinity. That's negative infinity over infinity. So that is an indeterminate form, which allows me to use L'Hopital's rule. So I'm doing all of this natural log and substitution to get to a place where I can use L'Hopital's rule in a fraction form. So my L'Hopital is going to be the derivative of 1 over a times the chain rule of 1 over a, which is negative 1 over a squared. So that numerator looks kind of complicated, but it's going to clean up for me. And then my derivative of my denominator is 1. When I clean up the numerator and multiply by the reciprocal, I end up with negative 1 over a, and that's all. That's all that's left after I've simplified. And when I substitute infinity into that, I'm going to get 0. So to simplify what we've got, we have the natural log of L to be equal to 0. When I apply an e on both sides, I get the limit is e to the 0, which is 1. So the limit to this equation is proven to be 1. And our last one, the form infinity to the 0. When I plug infinity in here, I'm going to get infinity to the 1 over infinity, which is infinity to the 0, which is our final indeterminate form. And we're going to use one more logarithmic application. So the natural log of the limit will be the limit as x approaches infinity of 1 over x pulled in front of the natural log of x. Now this is already a quotient. I can write this in quotient form, and that will show the indeterminate form. So I get the natural log of infinity over infinity, which is the indeterminate form infinity over infinity. So now I can use L'Hopital legitimately. So my final L'Hopital is the derivative of the natural log of x, which is 1 over x times 1, over the derivative of the denominator. So it's really just 1 over x. Plugging in infinity, I get 1 over infinity, which is 0. So again, the natural log of L turned out to be 0. So L must be 1. Oh, I said noon. It's only 11:55. Great, we finished that quickly. All right, so thanks for hanging with me on these 2 lessons. Thursday will be a review day, asking questions, and Friday is your test. So I need to know if you're coming in to sign up. Stephen, you said you were coming in, but you haven't signed up on the Google Doc yet. So could you do that for me so I know what time you're coming? And if anybody else, Andrew maybe, or Gabby, sometimes you guys come in. If you're going to come in, just let me know what time. And the rest of you have your parent or guardian email me back so that I know that they are on board for Friday. Okay? All right, that's all I have. Good afternoon, and I'll see you Thursday. Yeah, Andrew.
I think I signed up. Did I not?
Let me check my desktop.
I wasn't sure. I just wanted to double check.
I don't see you. Did you use your VC Schools account? Because if you didn't use VC Schools, if you were in a different Gmail account, it won't save.
Maybe I will do it.
Yeah, and you know what? Steven signed up on the wrong. He signed up for next Friday instead of this Friday, so I'll have to. Oh, yeah, it just showed up now. I saw it, Andrew.
All right. Thank you, Dave.
Okay, and I'll let Steven know too. Okay, thanks. See ya.